Alright guys, so today we're looking at an introduction to kinematic quantities. Alright, so we're going to be looking at things like distance versus displacement, velocity versus speed, and acceleration. We're going to try to understand as best we can what each of those things is. Alright, now introduction to that, really we need to make sure that first we understand the difference between a vector number and a scalar number. Now you probably should have studied this already. If you haven't, then you probably want to go look for a video that kind of really gets into detail about what the difference between a vector and a scalar is. But just as a basic introduction, vector is a number that has both a magnitude and a direction. If you remember the movie Despicable Me, it's got the bad guy Vector, and he commits crimes with magnitude and direction. So anyway, a scalar number is just a value, it just has magnitude, right? So a scalar number is like saying that I have a mass of 5 pounds. It just says that's what number it is. I have 5 cookies, right? It's just a number that says something about something. When you make it a vector, then you also give it a direction. So not only does it have a certain value, but it has to be either headed in a direction, or it could be a positive, negative, which sometimes gives direction as well. So there's various ways you can give a direction, but basically that's the idea, is that vector includes direction, and that's the important part of it. So remember which ones are vectors and scalars today, because if it's a vector, you'll always need to include some type of direction when you give an answer. So first we're going to talk about distance versus displacement. All right? Now, you probably know what distance is. Distance is how far you've gone, right? So, you know, if you were to run around a track, a typical running track is 400 meters, or about a quarter of a mile. Okay, so if you were to run around the track at your school once, except for the track here, which is like a 1/10 of a mile. But anyway, if you were to run around a normal track, it's about a quarter of a mile, 400 meters. So if you run all the way around, your distance would be 400 meters, because that's how far you've traveled. Distance follows your path, and that's it. You don't have to say how far you went, in which direction you're going in, or anything like that. You just say, I ran a distance of 400 meters. Now, displacement needs to bring in a direction. Now, generally speaking, when we talk about displacement, we're talking about our overall displacement from our point of origin. Okay, so if I were to go around the track and I were to start, here's my track, goes something like this. If I were to start here and run all the way around, that means that I would have traveled a distance of 400 meters, but my displacement from my beginning point to my end point, the change is 0. So displacement only considers the final and the initial. It's a straight line from your beginning to your end, and that's it. So if your beginning and end are the same place, then, well, your displacement would be 0 meters. And since it's only 0, we don't really add on a direction there, because you're just in the same place that you started. But let's say for a minute that you ran halfway around the track. Okay, so I started right here and I run halfway around the track and stop right there. Again, if I want to talk about distance, I went half the track, distance is 200 meters. But if I talk about displacement, displacement is just what's the difference between my starting place and my ending place. All right? And so that would be a vector that looks like this, starting here and ending there, which I don't know the scale, but probably about 60 or 70 meters, and then straight whatever direction that is. Maybe that's north. Okay? Now, in fact, we're usually not going to use north, south, east, west. Most of the time we'll just use angles. And so if we define the horizontal as being 0 degrees, we could say that that would be 60 meters at 90 degrees, saying that it went straight up from our point of view. All right, so that's the idea between distance and displacement. I hate running track for exactly this reason, because I run and run and run and run, and I get to the end, and what have I accomplished? I've accomplished a lot of nothing. I'm really tired, and yet my displacement, if I end in the place that I started, is still 0. Never accomplished anything at all. All right? Another place where, you know, this is important is, let's just say that you're going on a hike, right? And you're going on a hike and you're hiking up a really big mountain. But anybody who's gone hiking on a big mountain before knows that you don't really go straight up most of the time. You take a trail, and the trail goes something like this. It goes this way, and then it goes that way, and then it goes back this way, and just keeps on zigging back and back and back and forth until eventually at some point you go straight up to the top. What you find generally is that you may go on a hike which is 3 miles, and yet you've only gone up, 3,000 or 4,000 feet, okay, which isn't even a full mile. And so basically that's your difference between distance and displacement. Your distance could be, say, 3 miles, and your displacement would be 4,000 feet up, right, essentially. You could add in angles and make it more complex, but you get the idea, is that displacement is only your final and initial points, straight line between those, and a direction, okay? And that's it. Now let's move on to the second set, which is velocity versus. So one other thing really quick is that very often if we assume our starting point to be 0 or the origin, then displacement also gives us the position. So a lot of times you'll see a graph which is position versus time, and position essentially is your displacement from the origin. So just remember that. That'll be helpful when you're doing graphs and things like that. All right, so now next thing we're going to do is we're going to talk about speed versus velocity. Okay, and same thing. These are generally used interchangeably, but they're not really the same thing. They're close, but just like distance and displacement, speed right here is a scalar number, which means it just has a magnitude. I'm going 25 miles an hour. Velocity is a vector, which means a couple of different things. Number one, velocity being a vector will only be velocity from beginning to end. It'll be a straight line, okay? Velocity will also have a direction, being a vector. And so, going back to this idea of my track, if I were to run around my track in 4 minutes, we said it was 400 meters, then I could find my speed by taking that 400 meters and dividing by 4 minutes, which would give me 100 meters per minute, which, yes, is really slow, but deal with it. That's the example I gave. Okay, that would be my speed. Now, my velocity is from beginning to end. So if I start and end at the same place, velocity is generally, or average velocity, is generally defined as, so velocity average is generally defined as your displacement divided by the time it took you to cover that displacement. Now, generally speaking, distance will be a d, displacement will be shown by an s. Please don't ask why. I have no idea why it's an s. I'm sure you can look it up on Wikipedia or something if you really cared. I don't, so I assume that it was something about some Greek thing that somebody, it's some Greek word or something. I'm a physics teacher, I'm not an English teacher, so I don't care. Anyway, on to velocity. So that will be our velocity average, will be our displacement, s, divided by our time. And sometimes it's shown as a delta s, and delta is just the change, so it's the change in your displacement. In this class in IB, we're often going to kind of make the assumption that we're starting at the origin 0, 0, or that the initial starting point is 0, and so therefore delta s, s, final displacement are really the same thing because I subtract the initial, which is 0, and so, you get the idea. Define things, the way that you define things in this course is going to be important. Basically, we're going to define time 0 as being a displacement of 0, the starting point. Okay, so we've got our average velocity, which would be our displacement over our time, or our position over our time. Now, in the case of the track, if I were to run all the way around the track, we talked about if I go all the way around the track, my displacement is 0. And so if I were to find my average velocity for going all the way around the track, my average velocity would be 0 over 4 minutes, which would be 0. Now, a lot of people have a problem with that. They say, well, how in the world can my average velocity be 0 meters per minute? I was moving the whole time. In fact, I was booking. No, you weren't booking it. You were running 100 meters a minute. That's not booking it. That's pretty slow. You walk that fast. Anyway, but the idea is you were moving the whole time, and yet your velocity, your average velocity, ends up giving you 0. How do we do that? How does that even make sense? Well, if we consider the fact that here at the bottom, I'm moving in this direction, all right? And then as I go around the track, at this point, I'm moving in this direction. Note that my vectors are approximately the same size, so they're pointing in different directions. That's because the length of a vector is its magnitude. And so we go up, all right? I'm going around the track, I keep going and going and going. At this point, I'm now running in this direction, still the same size. And then as I get here to the corner, I go in this direction. Now really, there's vectors all the way around, but just for simplicity's sake, I put those 4 on there. What I want you to see, though, is that we can take these vectors, this vector right here, when I add it to that one, they actually cancel out, right? Up and down, they're exactly the same length, opposite directions, they cancel each other out. Same thing with these. I've got that vector to the right, that vector to the left. They cancel out, giving me a total of 0. You learned how to add vectors, right? You take the vector from here up, and then you go head to tail, so you take that one and go right back down, the vectors add up to 0. So if your velocity vectors all add up to 0, then that means your average velocity was 0, and you're still at the same place that you started. It doesn't tell you anything about what happened in between. It just tells you where you are right now, what's happening right now. Well, my average velocity was 0 because I ended up back where I started. Okay? Now, if I were to do the second situation, remember I talked about running halfway around the track. Okay? If I go halfway around the track, then, well, if I want 4 minutes for the whole track, let's just say 2 minutes. Again, my speed will be 400, not 400 meters, I'm only going halfway around the track, so 200 meters divided by 2 minutes. We'll assume I'm going at constant speed, which shouldn't be that hard. My speed is remaining constant. My velocity, though, obviously is changing the whole time. Okay, so my velocity, average. Okay, now notice that now going this direction and that direction, those will still cancel out, but in the middle I've got some other pieces that are going to come into play, and very specifically I've got this one, which at a point I'm just going straight up. If you were to add all those vectors together, what you get is your final displacement, which we said before was about 60 meters or so. We'll just continue to use that. So I've got a displacement of 60 meters, and then my time, which we said was 2 minutes. So my velocity average would be 30 meters per minute. All right? So basically we're looking at this idea of velocity being a vector, meaning that we take our displacement, or the total, not distance, but the difference in our positions at those 2 times, and then we divide it by the amount of time it took us to go that. Okay? So it really doesn't matter. Vectors don't consider the path that we take. Okay? Now, if I'm running around the track and all of a sudden a little bumblebee comes around, and I'm deathly afraid of Bumblebee now, obviously, because of this shirt, the Bumblebee's going to chase me all around, all over the place, and so I'm going to be like, ah! And I'm going to be running really fast now because I'm trying to get away from that Bumblebee. And that Bumblebee's just chasing me around, I'm going, ah! And I loop around, I go back, and after 2 minutes, I'm on the other side of the field. My speed during that time would be considerably more than 100 meters a minute because I was booking it trying to get away from that Bumblebee. However, my average velocity is going to still be 30 meters per minute because my initial and final points are the same through the same amount of time. I think I said 2 minutes. If I didn't say 2 minutes, that's what I meant. All right? So the idea is that velocity just considers beginning and end. It doesn't matter. It's exactly the same thing as if I were to just walk straight up. And I think I've said that enough times now that I'm not going to go through it again. So we got this idea of distance versus displacement. Remember, scalar versus vector. Vectors have to have magnitude and direction. And then we've got speed and velocity. Now, one thing that I should mention before I go on is that we often talk about 2 different types of velocity. One is the average velocity, which is what we've been calculating. We also have instantaneous velocity. Now, the instantaneous velocity is how fast am I moving and in what direction am I moving right this instant. And that is almost the same thing as speed. The value, the number, will be the same as the speed. What will be different, however, is that with velocity you also need a direction. That's right, because it's a vector, it needs both. And so if I were to look at the instantaneous velocity at this point right here, as I'm running around the track at my normal 100 meters a minute, then I could say right here that my velocity instantaneous, V-I-N-S-T, or you can label it however you want, just make sure that it's clear. Your velocity instantaneous would be 100 meters per minute. And I know that because that's my speed as I'm going around, the same thing, at, and again I'm going to say 90 degrees because I'm going up. And you can call it, you know, if you have another direction, you can call it another direction, but that's just the convention I'm using right now. Okay, so we got average velocity, we got instantaneous velocity. Okay, now what we want to go into next is one last thing. We've got our distance, displacement, velocity, speed. Last of all, we've got acceleration. Okay, so now we want to talk about acceleration. And we're going to keep some of this here because acceleration is going to tie into this. What acceleration is, no, it's not speeding up. Somebody at some point in time said, if you're accelerating, you're speeding up. And I'm here to tell you, no, that's not right. Acceleration is a change in velocity. And I'm going to use the triangle, that's your delta, which you've probably seen in some science class before, or math class. I mean, you use it all the time. So a change in velocity. Okay, that is the definition of acceleration. Don't let anybody tell you otherwise because they're lying if they do. All right? Now, this is going to kind of bump into a couple other things. For example, deceleration, we don't use that word. All right? Deceleration is a flibbity-gibbet word come up by some English teacher somewhere because they don't understand acceleration. All right? Deceleration people often use for slowing down. But if you are slowing down, you are changing your velocity, which means that that is really acceleration. Okay? So deceleration is a word that was construed in the English language to mean slowing down. Acceleration is not the opposite of deceleration, and we will likely not use deceleration in here. If we do, then what you should recognize is that word deceleration only means slowing down, and it has to mean slowing down. Acceleration, however, is much more comprehensive because it can be slowing down, it can be speeding up, it can also be something else. How else could my velocity change? We could have the velocity increase, you could have the velocity decrease, you could also, remember velocity is a vector, so therefore, if my velocity changes direction, my velocity is changing, and therefore, I'm accelerating. That's acceleration. So, acceleration being a change in velocity. All right? So, generally speaking, when we calculate acceleration, it'll be the same. We're going to be finding an average acceleration. Most of the time, we are going to consider that acceleration is constant. And so the average acceleration is the same as the instantaneous acceleration because it's not changing. But we'll deal with that when it comes. So for now, we're going to say acceleration or average acceleration is going to be your final velocity minus your initial velocity, or the change in velocity, whatever you want to say. So final velocity minus initial velocity divided by, time. Okay? Now, the initial velocity you can do with a V naught, V0. Often it is also, and how we'll do it in this class, a lot of times we'll use a U. And so a lot of times what you'll see is A equals V minus U over T. So don't be confused. U is just the initial velocity, and the V that doesn't have any number is your final velocity. And that's how we'll calculate acceleration. That will give you the number, obviously. Acceleration is also a vector because it's any change in velocity. Okay, so as we get to other things, we're looking at, you know, this problem we were looking at before. My velocity originally was to the right, and then when I get halfway around the track, my velocity is now to the left. So the velocity has changed. Even though the speed has stayed the same, my velocity has changed. So if we look at it mathematically, how are we going to do this subtraction of the vectors? Well, we learned how to do that previously. You should know if my first vector is going to the right, so that's my first vector, which was 100 meters per minute, right? And then my second vector at the end is going this direction, so that's 100 meters per minute. Now to the left, okay, if I subtract those, remember when you add, you go head to tail. When you subtract, it's the same thing as adding a negative. So if I want to do v minus u, that's the same thing as doing v plus a negative u. And that's usually the easier way to do it, because then we just switch the direction of the vector and we go head to tail. So my final velocity is this one right here. Okay, so that's the vector going in that direction. And then I'm going to add to that a negative u, and this is my original velocity, right? This was the final, that was the original from looking at my picture up there. So that means that I'm going to get a negative u, which is going in this direction. I'll add head to tail, which means I'll have 100 meter per minute that direction, 100 meters per minute in that direction, which means when I add that together, I get a total of 200 meters per minute to the left, or at 180 degrees, or whatever you want to call that. If that's a direction, you can, if that was north and that was probably west. Okay, so you can then give a direction to that. And you notice that even though my speed didn't change, I have a significant acceleration of 200 meters per minute. Now, that has to be the case, because if my acceleration was 0, then my velocity would still be 100 meters a minute to the right like it was before. That's not the case. It's now going to the left. So it had to accelerate 100 meters a minute to the left to get down to 0, and then another 100 meters a minute to the left to be able to go a velocity of 100 meters per minute to the left. And so that's my acceleration. Now this can lead into some interesting things when we start changing direction, just like we just talked about. So if I'm going from right to then going straight up, that's now going to give me an acceleration in a different direction, not even parallel to the other two. And we'll look at more at that when we look at some more problems. But for now, what you need to recognize is the fact that acceleration is a change in velocity, any change in velocity. All right? Now, a couple of things I want to mention just in wrapping up, okay? You need to know what positives and negatives do, okay? Generally speaking, we use positives and negatives to denote a direction. It denotes a direction when we're only going directly horizontally or straight up and down, right? So if I'm going horizontally, then a positive value would be going to the right, okay? A negative number would be going to the left, okay? Or that vector is in a direction to the left. If I'm going up and down, generally speaking, up will be positive, down will be negative. And it's important that you put those positives and negatives on there because we have to include the direction. And that's a way to simplify it. If I'm only going up and down or only going to side, it's a way to simplify the direction so I don't have to be saying up or down or whatever, because the positive negative will make the math a little bit easier. Okay? So with that, I want to recognize what do each of those things actually tell us about the object. Okay? Remember, displacement is essentially position, because we're saying that it starts at a position of 0. So if I have a positive displacement, all that tells me is that, for example, I'm to the right, or I'm above of my origin. Okay, it doesn't tell me anything other than that. It doesn't tell me how fast I'm going. It doesn't even tell me which direction I'm going right now. It just says that right now I am to the right. Okay, or I am above where I started. Okay, you have to remember that because it does not tell you which direction you're traveling in. A lot of people would say, well, if my displacement is positive, so I start here, I'm going up my mountain, and I'm right there, my displacement is positive, so obviously I'm going up, right? Because my displacement is positive. Not necessarily, because think about this. You start here, you hike up the mountain, you get all the way to the top, and then you start coming down, and you stop right there. Your displacement is still positive because you're above where you started, but what direction are you heading now? You're actually starting to head down. And so your direction is actually negative. It's going down. So remember that a positive displacement doesn't necessarily mean that you are moving upwards or that you're moving to the right. It just tells you where you are. Okay? Now, velocity, that's usually the big one, because velocity tells me how fast I'm going and what direction am I moving right now, right? Because your velocity is the change in your position. Velocity is change in displacement. And so if you have a positive velocity, it means wherever you are moving in the positive direction. So you're moving to the right or you're moving upwards. Okay, so that's important to recognize that positive velocity means that you're either moving up or to the right. Negative velocity means either down or to the left, as long as we're staying in our two-dimensional world. Okay, which we will a lot of the time because it just kind of simplifies things, and that's the scope of this course. Okay? Acceleration, a positive acceleration means that the velocity is changing in the positive direction. If you have a positive velocity and you have a positive acceleration, it means it's becoming more positive. Now that generally means that you're speeding up. But what if you have a negative velocity? Negative velocity means that you're actually traveling to the left. I'm traveling to the left. If I have a positive acceleration, the acceleration is in that direction. It doesn't mean I'm moving that direction. Velocity is telling me which way I'm going. I got a negative velocity, I'm moving in this direction. A negative acceleration though, negative velocity, positive acceleration though, is telling me that the velocity is changing in that direction. So it was highly negative, and as I have a positive acceleration, my velocity is going to become less negative. It's going to become close to the positive. So if you have a really big negative number and you become less negative, you're getting closer to 0, which actually means that you are slowing down. I'm still moving to the left, but slowing down. Now, as soon as I stop, if I still have positive acceleration, it's going to make me go more positive, and therefore I'm going to go this direction. Now I'm going to speed up. Okay, so it's important to recognize that acceleration doesn't tell you which way you're moving. All it tells you is how is your velocity changing. Is it increasing in magnitude? Is it changing direction? That's all acceleration tells you. Just like displacement only tells you where you are. It doesn't tell you which direction you're going. The direction you're going comes from the velocity. If you don't know the velocity, you don't know what direction you're moving. That's all we can say. All right? If you have any questions, shoot me an email, shoot me a comment, what a comment, blah, blah, blah. I can speak really. So whatever, let me know, and hopefully that's helpful.